Okay, welcome back to EE210B. We are going to continue our discussions of inference over networks. In the last lecture, if you recall, we discussed the network model, right? I introduced the network model, and I mentioned that we will be focusing on strongly connected networks. These are networks where if you pick any two arbitrary agents, you can find a weighted path that takes you from one agent to the other, and also that can bring you back. The paths do not need to be the same, right? And for strongly connected networks, I showed that the combination matrix A is primitive, meaning that it will have a single eigenvalue at 1. All other eigenvalues will be strictly inside the unit circle. It will have a Perron eigenvector P, whose entries we normalize to add up to 1, and whose entries are always positive, right? So this is just some of the results we proved last time. So last time was focused on the model, the network model. Today I'm going to focus on the algorithms that we are going to run over that model. Okay, so what are the algorithms? Okay, so that's what the title of this lecture is. Okay, and the material is based on these two references, chapter 7 from the text, and also I will cover some information from Appendix E from the second reference, both of which you can download from my website. So if you recall, okay, in the last lecture, I mentioned that we are interested in this problem. I have n agents, so capital N is the number of agents. Each agent has a convex function j sub k associated with it. K is the agent index, and we would like to find the minimizer of the aggregate sum. Since we assume that the aggregate sum is strongly convex, not just convex, strongly convex, meaning that the Hessian matrix of the aggregate sum is sufficiently away from 0, so it's positive definite with sufficiently away from 0, then this cost will have a unique minimum, which we are denoting by omega 0. Okay, so now over a network where agents only have access to their individual j sub k and to the j sub k's of their neighbors as well, if necessary, but not to all j sub k's, how do you develop strategies that allow the entire network to learn what omega 0 is, right? This is one of the main objectives that we'll be talking about, okay? Now, in this lecture, I will be talking about 3 classes of strategies that are widely used: incremental strategies, consensus strategies, and then diffusion strategies. And I will explain what the differences are, okay, and what are the properties for the purposes of adaptation and learning. These numbers that you see here are just references in the text to many articles related to these topics, okay? Very good. So let's start. So I have a problem that's well formulated. I have an aggregate cost, which is the sum of individual costs. I would like to find the minimum, right? Now, if I give you that problem, and I ask you to write down a gradient descent algorithm to estimate that minimum, you would write something like this. Okay, so what do you have here? I have the new, right? So the new estimate is the old estimate minus a step size, right? I'm choosing the step size here to be mu divided by n. I'm scaling it by n. I'm free to choose the step size, so I'm just writing it in this form. Okay, and then the gradient descent would use here the gradient of that aggregate sum, which is the sum of the individual gradient vectors. So the sum of the gradient vector, since I'm allowing omega in general to be complex valued, I explained before that in this general case, you compute the gradient relative to omega star. In the real case, it would be just relative to omega transpose, right? So the gradient evaluated at the current estimate. Now, in the stochastic case, where I don't actually have the j sub k's, because like I said many times before, very often we will be dealing with the situation where the risk function has the form as the expectation of some loss function, right? Some loss function depending on some data x, right? This is data x, okay? And this expectation is over the distribution of the data, right? Like mean square error costs, right? So Q will have the form d minus uw squared, right? Expectation. D and U would be the data, W is the unknown. So in general, you do not have the distribution of the data, which would prevent you from knowing actually what J sub k is. So we said in that case, I do not know what the actual gradient is. Instead, I'm going to replace it by an approximation, right? And the approximation usually is simply to use the gradient of the loss function itself, right? Because Q, you know, Q is simply this, right? Remove the E is simply based on the data, right? So now we are using the sum of the approximations as an approximation for the aggregate gradient. That's what we are doing here, right? Like this is the centralized solution, right? If you were to solve this problem in a centralized manner, I have a fusion center that knows all the J sub k's and knows how to approximate them. This is the recursion it would run to try to converge to omega 0. In an earlier lecture, we studied the performance of centralized solutions like this. And we showed that for step sizes that are small enough, the omega will converge close enough to omega 0. Remember that? We showed that the variance of the error, which is the difference between Wi and Wo, right, so the lim sup, right, as I goes to infinity is of the order of mu. So if your step size is very small, you get very close to it, right? This is what we showed when we studied centralized solution. So let's start from this centralized solution. Of course, now we are interested in a distributed solution over a network, right? This is not what every agent cannot run this, because every agent only knows its J sub k, and at most the J sub k's of its neighbors, but it doesn't know all of them. Okay, so, but we are going to start from this recursion, right? I'm just repeating it here. We are going to start from this recursion and use it to motivate distributed strategies. So I'm going to derive the distributed strategies in one particular form. There are many other ways by which you can derive these strategies more formally, right? I'm going to derive them in a more intuitive way, okay? I don't need to derive it very formally, right? I just want to get them from the centralized solution, motivate them in an easy way for you, and then later we are going to study their performance in great detail, okay? So let's start from this centralized solution, and I have a network just like you see here on this slide, okay? And I would like to derive a distributed solution instead, okay, that allows the individual agents with limited knowledge to arrive at the same conclusion. Okay, so this is what we are going to see. So I start from the centralized solution that I have here on top, okay? Let's do the following. I have n agents, right? I have n agents in my network. Let's number them. Let's say agent 1, agent 2, agent 3, and so forth, right? Let's number them from 1 to 5, okay? And let's assume that I have, so you have some topology linking them, okay? Have some topology linking the agents, okay? I'm going to number them from 1 to n, okay? And this is what I'm going to do. I'm going to start from agent 1. So agent 1 starts from the current estimate, right? This is what I have, Wi minus 1, okay? You see, this is the centralized solution. The new estimate is the old estimate minus the sum of gradients. I can compute this update by asking every agent to add one element of the sum. So here it is. Agent 1 starts from the initial point, adds to it the first gradient, because it knows that information. I mean, it has that gradient, right? This, at agent 1, will give you this intermediate value, which I'm calling W1, to say this is computed by agent 1. Agent 1 now passes this information to agent 2. So this goes to agent 2. Agent 2 receives this, adds to it its gradient, and that generates an intermediate value at agent 2. Agent 2 passes it to agent 3. It adds its contribution, right? By the time you are done, right, the last agent is going to add its contribution, and by the time you are done, you have gone from Wi minus 1 to Wi, correct? So this implementation is equivalent to that implementation. Do you see it? Nothing changed, right? Every agent is contributing to computing that sum. By the time you arrive at agent n, so here you start with Wi minus 1, at agent 1. By the time you arrive at agent n, you will have the Wi that you wanted. And now you repeat. Wi moves to agent 1, and then the process repeats. Fine? So nothing changed so far. Is this a distributed implementation? Okay, if you look at it, it's not a distributed implementation. Why? Because for a subtle point, all agents need to know the same piece of information, which is the initial estimate that you started from. Right? This is what you have here. In this implementation that you have on this slide, there is a common piece of information that everybody in the network needs to know. How are they going to get that piece of information? This is a global piece of information. If you say it's available at 1 and everybody else needs to know it, then one needs to share it with everybody else. So this is not a distributed solution. In a distributed solution, I would like every agent only to use information it has available from its immediate neighbors, okay? And that should be enough. Understood? Okay? Of course, in this particular example, all nodes happen to be neighbors of 1, right? But you can, right? Let's add another node here. Let's say 4, node 4 here, which is only neighbor, right? Sorry? Oh, sorry, yeah, 3. So 3 and 4, right? You get the point? So this is not distributed. How do I make it distributed? That's the main idea of the incremental strategy. What the incremental strategy says is this. Look, agent 1 did its part. So in principle, this is an improved estimate over that because I already added some information to it. So when I pass it to the next agent could use it here instead of Wi minus 1, right? And then this gives you an intermediate estimate. You pass it to the next agent. The next agent would use this here and also here. So that's the key idea of the incremental step. So you do an incremental step, and that update, you use it for the next step, and you keep going, right? So if I write this, okay? So this is just explaining in what I explained before, right? That all of them need a global piece of information. So here it is. So this is what I have. I'm going to replace it, but what agent K received from the previous agent K minus 1, right? This is the summary of the step that's being done at every agent. At agent K, you receive the information that agent K minus 1 has, right? The intermediate estimate, and you use it both here and there, right? This is how the incremental step looks like. Fine. So this is an example. I have a network here. I start by numbering the agents 1 through n, and I start by finding a cycle that goes through, that visits all the agents, because I have to visit all of them and restart, right? So you have this additional step that you need to do, which you will not need to do when we study consensus and diffusion. But in incremental, you need it. I give you a network, you have first to find a cycle that visits the agents, and you have to number them 1, 2, 3 through n. Okay, so this step we will not need it in consensus and diffusion, and this is not a trivial step, because in general, if I give you any arbitrary network, it's not easy for you to go and find a closed cycle that visits all these agents once. Okay, that's number 1. Number 2, observe that you are going from location k minus 1 to location k, right? So it's k here that's changing, right? Not I. Okay? Because I start with W at I minus 1 here. I have to do n steps of calculations to get Wi, right? So between 2 time updates, you have to do n steps of calculations, right? This means that if your data is arriving at every I, between 2 time arrivals for the data, you have to cycle through n agents. So the processing at these n agents has to be done n times faster than the arrival rate for the data. Before the next data arrives, you should have processed n agents, right? So in this implementation, the agents will need to have more processing power than is actually needed, as we are going to see. In consensus as diffusion, you will not need that. The processing can be done at the same rate as the data arrival. You see this point, okay? So these are some of the subtleties that come up in the incremental implementation. That's why I will not be spending too much time talking about it in the context of adaptation and learning, because this is a problem for adaptation and learning. First of all, the agents have to be more powerful than you really need them to be. Second, you have to find a cycle that covers all the agents, and this is not always an easy task to do. And third, even if you succeed in doing that, if one of the edges in this cycle breaks down, then the algorithm breaks down, right? If this edge breaks down, you cannot run the algorithm anymore, right? Anyway, but this is the incremental idea, okay? I'm just summarizing the algorithm here. What you get from agent k minus 1, you pass it to agent k, and you keep going. By the time you arrive at node n, that's the wi, and then you repeat. Okay, this is just a summary of the algorithm. Yes.
So after the learning process and the last iterate,
yes,
the last agent will have a different weight than the first one, right?
Sorry, after?
Say, like you're doing this learning process for finite duration.
Yes. So,
the last one will have a different weight.
Exactly right. But as I goes to infinity, you expect all of them to get close together, okay? Not the same, but they will get close together.
And the flow of, like, the order doesn't matter, right?
It follows the numbering that you chose, right? You may choose it this way, you may choose it that way. Of course, the ordering will matter in that the intermediate estimates at the agents will be dependent on what you get from the previous agent, right? If your previous agent is this one or that one, it will alter your estimates, right? It does matter, okay? But hopefully in the limit, as time progresses, all these differences will disappear, right? Okay, so here I'm just representing. So you start with a network like this. You find a cycle and you renumber the nodes, and then you run the algorithm, okay? So this is agent 5 to get the estimate at 6. You start from that location, compute the gradient at that location, you add them together. Right? This is just a graphical representation, okay? Very good. Now, if you want to specialize this to LMS, for LMS, the cost is the quadratic cost, right? Expected value of D minus UW squared. If you remove the E and use only Q, to find the approximate gradient. When you differentiate relative to omega, you will get this 2, right, times d minus uw times u, right? This is the gradient relative to w. All this h is saying if I'm working with real data, when you differentiate, you get 2. But if you are working with complex data, when you differentiate, as we saw before, differentiation relative to complex arguments, you're not going to get that 2. So this h is just a type variable so that I capture both situations in one equation. When h is 2, you are handling the complex case, it cancels that 2. When h is 1, you are handling the real case, so you get the 2. Okay, so this is just to address both of them together. So this is how the incremental LMS would look like, okay? You see, this is the weight from the agent before you, the weight from the agent before you. You receive that, you add your own data, because you are computing your own approximate gradient at that location, you update and you get that, right? But I explained to you already what's the problem with the incremental solution, right? So the incremental LMS is applied over this mean square error network, right? Where each agent receives D's and U's, and then you apply incremental LMS, okay? And the problems I already explained to you, that if a link fails, then you cannot run incremental anymore. Determining a cycle is not an easy problem. Cooperation between agents is limited. Why? Because I'm an agent, the only information I'm seeing is just what comes from the agent before me. Okay, is limited, and I need to perform n iterations before I can repeat, okay? Very good. So, because of that, I'm going now to motivate a different strategy, a popular strategy known as consensus, okay? This is not how it was originally motivated, but I want to use this motivation that I'm explaining here just to keep the presentation flowing and simple, okay? So now, if you look at the incremental update up here, and like I said before, you can derive these algorithms more formally by solving well-defined problems, okay? But I don't need to go that far to motivate the algorithms, okay? Because we are not interested, we are more interested in seeing what performance we can get from these algorithms, okay? Now, this is the incremental solution, right? Agent K receives a vector from the previous agent located at location K minus 1, evaluates the gradient at that location, and then the update gives you WKI, and then that passes to the next, right? Now remember, so this component corresponds to cooperation. This is where cooperation happens between one agent and another. You tell me what you have, and I'm going to use it. So this component helped with cooperation. When I put it here, my purpose was to make sure that the implementation is a decentralized implementation, distributed implementation, right? So that's why I say this component helped with cooperation, and putting it here helped make the solution decentralized, okay? But now when I go to consensus, right, now you give me a network, Now there is no reason why I should limit my cooperation to my immediate neighbor, right? I can cooperate with all of my neighbors, okay? So for example, I can replace this item here, which is what he's sending me, by an item like this. Let's look at this item. What this is saying, right? I'm not only looking at K minus 1. I'm looking at what all of my neighbors have, right? L is in my neighbor. I have 5 neighbors. I compute a convex combination of all of my neighbors, right? By using a convex combination, you are not introducing bias, because the average of this, right, would be the same as the average of the individual estimates, right? So I use a convex combination of what my neighbors had, okay? Of what my neighbors had. Now, here I was the same as this I, because between 2 time instance I'm performing n steps, right? So all these steps were still being performed at the same time instant. As you are going to see when I go to consensus and diffusion, I don't need anymore to perform n steps between 2 time instants, okay? So that's why what I'm saying here is just combine whatever estimates my neighbors have now at this time instant, okay? And update that along the negative direction of the gradient vector, okay? Negative direction of the gradient vector evaluated at my current estimate, okay? So I'm agent K. My current estimate is this value, fine? This is my WK at time I minus 1. You see, this is different from this, okay? I'm agent K, and I want to run a gradient descent update. So I'm going to evaluate the gradient vector at what I think is the best estimate at this point in time, before I waited for the other person to tell me what it is. Okay, so this is my estimate, and then I'm going to look at the estimates across my neighbors and use that as a starting point. Okay, this is what consensus does. That's it. Okay, it uses a more enhanced cooperative term, and it moves along the direction of the gradient vector evaluated at where I am now. Okay, now you can see here that I replaced mu over n by mu. Right? I don't need to scale by n. Why is that? And you are going to understand this better once I show you the diagram and explain the algorithms, both consensus and diffusion, more fully. Okay? What happens is, remember when we studied this centralized solution and compared it to the non-cooperative solution, a single agent running gradient descent and the fusion center running gradient descent, I used a step size mu there and a step size mu over n here. What was the reason there? So that the convergence rate of both algorithms are the same, and you compare their performance, right? Because when you want to compare algorithms, you have to fix one or the other. You either fix the convergence rate and compare their MSDs, or you fix the MSDs and see how fast they get there, right? The mu's here will play the same role, okay? By this mu over n came from the centralized solution, and you scale it by n to make sure that the centralized solution will have the same convergence rate as the diffusion and consensus algorithms that we'll be using with mu. Now, I'm not going to be proving this statement now. You'll understand this statement later. Later, I'm going to show you that a consensus strategy like this with mu, or a diffusion strategy similar with mu, both of them will have the same convergence rate as a centralized strategy with mu over n. Okay? That's why I use mu here and mu over n there, so that when we compare their MSD performance, we are comparing them under similar convergence conditions, okay? Another way for you to appreciate this is that, remember, I have to complete n of these steps between two time instants. I only perform one step here between one time instant and another. You see, at every time instant I, every node in the network is going to perform this update. Every node K starts from where it is, looks at where the neighbors are, and updates. Every node now does it at the same time, simultaneously. So in going from one time instant to another, I only did one update here. I did n updates here, right? N updates here. So obviously for the convergence rate to be comparable, you have to scale the step size by n, right? Because here you added n pieces of information between two time instants than here, okay? This is all informal justification. The formal justification will come later, okay? When you look at the expressions, you'll understand, okay? Okay, so this is what I call the consensus recursion. This is not the original consensus implementation, which I will be discussing later, but I'm already putting it in a form that is more suitable for adaptation and learning, okay? So you have here a constant step size by agent K. It can be the same across all agents, okay? So now, this is one way to write the algorithm. There is another way to write this same algorithm. I can call this sum some intermediate variable. Let me just look at the notation. Sorry, oh, wow, okay, psi. So I can call this psi k I minus 1. What you can write this recursion as two lines. First compute psi, which is the sum, and then start from psi and update it. Okay? This is another way to write this expression. Okay? Very good. So let's continue. Okay? So this slide is explaining the difference between why I use mu and mu over n, just because I want the convergence rates to match, and this will be shown later. Okay? I just try to give you some justification. And the main reason is that one implementation has n steps, the other has only one step, okay? Now, the coefficients A that you are using to combine the estimates of your neighbors, these are the A's I talked about last time, the A's over the graph. They are non-negative, they add up to 1. If I'm agent K, I have 5 neighbors. The weights I use with my neighbors will add up to 1, including me, AKK. Okay? And the weight will be 0 if you are not my neighbor. Right? These are the same weights I talked about last time. Okay? So, and I can collect these weights into a matrix A, and that becomes the combination matrix. And like you saw last time, each column of this matrix will add up to 1. Right? This is just reminding you. And so you see where this A comes from. Incremental does not have the coefficients A, but the consensus has these coefficients, right? Okay? So each column of A adds up to 1, okay? So here it is. So this is a left stochastic matrix. And if your network is strongly connected, then it is actually primitive, right? Okay, now, every left stochastic matrix, so true or false, every left stochastic matrix has a spectral radius that's 1. You know what the spectral radius is, right? The largest magnitude eigenvalue. Okay? And this is always true. Why? Because you remember when we reviewed matrix results for this course, we said that the spectral radius of a matrix, right, is upper bounded by any induced norm, right? For example, here for the column sum, let's take the 1 norm. Since the column, right, what is this? This is the maximum column sum. Since all columns have norm 1, sorry, add up to 1, and they are non-negative, so this is definitely 1, right? So left stochastic matrices, the spectral radius of left stochastic matrices, right, is always equal to 1, okay? Because we know that one of the eigenvalues is 1. Because of this relation, right? This tells you it's less than or equal to 1, but we know that one of the eigenvalues is 1. So, okay. I'm just reminding you of some properties, okay? this is just explaining how consensus works. Okay, so I think if I go to the next slide, which summarizes the algorithm, it's easier for you to understand. I have a network. This is the network. I don't have to find a cycle anymore. I don't need a cycle. Therefore, I don't need to renumber the agents. You just work with whatever you have. Every agent has its own cost. So this is how consensus works. At every time instant I, agents are receiving data. For example, in the mean square error case, each agent is seeing D and U, data D and regression vector U. More generally, right, they are receiving some data that allow them to compute the approximate gradient, right, which is the gradient of the loss function Q. Okay, so this is how it works. At every time instant I, every agent K, right, every agent K here looks at its neighbors and combines the estimates that exist at that time instant at the neighbors, and then uses that intermediate estimate psi as an initial point, right, and moves along the negative direction of its gradient or approximate gradient, right, starting from where it is. Okay, and this is where it is, and then you update it to WKI. This is what the consensus iteration is. Now, why it's called consensus, I'll explain to you later. Okay, for now, just know that this is how the algorithm looks like. Okay, and this is one way of motivating the algorithm, but again, you can make it more formal. Okay, we don't need to go to that argument. Okay, so every agent in the network is doing exactly the same thing at the same time, right? So data arrives, then this looks at the neighbors, combines them, and then takes a step. This one is doing the same thing. This one is doing the same thing, right? Okay. And every agent can use a different step size, or all of them can use the same step size, okay? So this is how consensus works. And this is down here, you have a representation. So for example, for agent K has neighbors 4, 7, L, and K. So here it is, 4, 7, L, and K is there. So it gets the weights from the neighbors, combines them, it goes here, and then it gets its own estimate, applies a stochastic gradient computation to it, combines them to update its estimate, and everybody else is doing the same thing. You understand? So you see, the combination is being done in parallel with the stochastic gradient update. Just remember that. Okay? Okay, so this is the consensus strategy. Why it's called consensus, I'll talk about it more later, okay? Now, so this is explaining in words what I just explained over the in the figure, okay? Now, if you specialize this to mean square error networks, right? So the approximate gradient, here it is, the approximate gradient is U times the difference. And then you have 2 over H, depending on whether you have real data or complex data. So you compute the intermediate estimate from your neighbors, and then you correct it by the approximate gradient. That's what each one of them is doing. You understand? Okay? So this is for the special case when your cost function is mean square error. If it is logistic regression, you'll get a different algorithm. If it is something else, you'll get a different algorithm, right? This one here is a very general implementation, okay? Very good. So here, this is again, I'm just repeating it. Okay, this is in the real case. For the real case, it looks like this. H is 1, so it will look like this, okay? Okay, so now let's move a step further, diffusion. This is not how we motivated diffusion when we first came up with this idea, okay? But this is a simple way of motivating it in the following the arguments I showed you, okay? So now, if you remember, incremental looked like that, okay? You had a cycle, you have to perform n steps between every 2 time instance. One element was responsible for cooperation, the other element was responsible for decentralization, right? Okay, and then from that we motivated consensus, okay? This is cooperation. We replace this cooperation by an enhanced form of cooperation. I'm still looking at what my neighbor, tell me what you have, I'm going to combine them and use that as a better initial estimate, right? for applying the gradient descent direction. So this is cooperation, right? And this is, of course, decentralization, because this agent only needs to know its own estimate to be able to move along that direction, right? So this helps with decentralization. Okay. However, observe that when we developed gradient descent recursions earlier, they always looked like this. The new estimate is the old estimate minus mu times the gradient of your cost at the current estimate, right? Or the approximate cost if you are talking about stochastic gradients. But the important thing in gradient descent recursions is that the point where you start and the point where you evaluate the gradient are the same, right? So for example, for quadratic costs, if you are here, then you will move along the negative direction of the gradient at that point to a new point, right? This is not happening in consensus. In consensus, you see, you can look, look at this. This is like, okay? So remember, I call this psi k I minus 1, right? So the new estimate is psi k minus 1 minus mu k gradient of the costs at wk I minus 1. So on the face of it, if you look at this, this looks very much similar to a gradient descent recursion like the one you have, right? Except that the point where you start is different from the point where you evaluate your gradient, right? So I call this asymmetry. You understand? There is an asymmetry here. Where you start, you are starting from a location which is different from the location where you are evaluating the gradient, okay? We have shown, and you are going to see in this course later, okay, we are going to study this analytically, that this becomes a problem in the context of adaptive solutions, in the context of adaptive networks, networks that use stochastic gradients to learn from streaming data that's arriving, like D and U, right? Or gradient of Q, that's based on the loss function. So when you are using an implementation like this in the context of adaptive networks, which therefore use a constant step size so that you enable continuous updates, this leads to instability problems. The network becomes unstable. Okay, meaning even if the individual agents, even if every individual agent is able to solve the problem on its own, running its own gradient descent algorithm independent of the other agents and is able to converge, if you connect them by a topology and apply consensus to let them work together to estimate that same minimum, the network will become unstable. I'm going to show that later, okay? So this asymmetry problem can cause instability for consensus, and I'm going to show you when this happens, okay? Now, so this was one of the motivations, right, to introduce the diffusion strategies, and there was other motivations as well, which I'm going to explain as we get there, okay? So the diffusion strategies, they do not have this asymmetry problem. They remove it. And then we're going to show later that if your individual agents are each individually stable, can solve the problem on their own, no matter how you connect them, the diffusion strategy will always remain stable. This is not true for consensus strategies in the context of adaptive networks, okay? You are going to understand these statements in future lectures, but I'm just mentioning them to you now. Okay, so for example, one way to remove the asymmetry problem, again, this is not how we derived these algorithms when we first did it, but this is one way to motivate them, okay? So one way to remove the asymmetry problem is to say, start from psi, but also compute the gradient at the same location psi, right? Of course, this becomes, if you do the analysis, becomes a little bit more involved to do the analysis for problems like this. But this is one way to remove the asymmetry, right? Because remember, I called this psi k I minus 1, and then this becomes the gradient, J, evaluated at the same quantity, right? This becomes wki. So this form of the algorithm, okay, so this part helps with decentralization, and this part helps with cooperation. This form of the algorithm, I call it combine then adapt. Why? Because this part here is doing combination, right? You have to compute this first. You have to compute the psi combination, and then you put the combination here, and you do the adaptive update, right? So we call it CTA diffusion. This is how this is called. Okay, so if you look at the statement of the algorithm, this is the statement of the algorithm. You combine, right? You combine the estimates of your neighbors, but then when you do the gradient update, you use a symmetric form, right? You use a symmetric form. You start from that location, and you also compute the gradient at that same location, right? So if you look in terms of the representation now, it's not anymore a parallel representation, but you have a series cascade. That's the change that it makes. You see, you use so you have these neighbors, you combine them to find the phi, right? And then you feed that same phi into the stochastic gradient block, and the combination gives you W. So you combine, then adapt. So now you have a series cascade, okay? Before they were done in parallel, okay? And so this particular change introduces stability, okay? And other things also, performance will improve, okay? But that requires some argument, okay? And especially when you go to the next form, which is the adapt then combine form, ATC. This is CTA, and then there is ATC. What's ATC? You see, once you look at this, there is no reason why. I'm an agent, right? I'm an agent K. What the agent K is doing here, first I look at my neighbors, I combine their information, and then I adapt. But I can reverse the operation. I can first adapt, and then combine. I first adapt, and then I share the updated estimates, right? And then combine. So this is the ATC version. The ATC version, agent K, you can see here in the first line, agent K first performs adaptation. So that only depends on its own data. And then it combines the estimates from the neighbors, right? So you adapt, and then you combine. You understand? This is like I giving you an exam. I like to give this example. I give you an exam, and I define a network, and I tell you you can solve the exam by talking to each other, only to those connected to you in the network, right? So there are two ways, or at least two ways for you to solve the exam problem. One of them is you first think about the problem yourself, right? This only depends on your data. And then you ask your neighbors, so what was your answer, right? First think and then talk, right? And in the previous strategy, let's first talk. But let's first talk, what do you think the answer is, right? And then I'll think based on the information you gave me, right? So which mode of operation do you think will lead to better performance? ATC, and we are going to show that analytically, right? Analytically, we are going to show for general costs, right? For general costs, that your intuition is correct, that ATC actually gives you better performance, okay? So this can be shown analytically. It requires some effort, but we are going to do that later in this course, okay? But the intuition, that's the intuition, okay? Because each one is thinking before talking, okay? Now, if you specialize these algorithms to mean square error, right, this just shows you some examples. You see here it is. This is the gradient, right? This is the gradient, 2 over h times that. It's the same here. So here you combine, then adapt. So you adapt starting from the intermediate estimate. Here you first adapt from what you know, and then you share the information, right? These are two forms, ATC and CTA, for mean square error networks. But the algorithm I showed you before is more general because you can use more general costs. Okay, so this is, again, I'm putting them together now, CTA and ATC. Okay. This is another example for logistic regression. If you are solving a pattern classification problem, right? I give you feature vectors H. So each node K receives feature vectors H and classes gamma, right? And you would like to find the separation, the separating hyperplane that tells you whether a new feature that they are going to observe belongs to this class or that class, right? This is similar to what we did in EE210A, but here you are going to solve it over a network, right? So you have a situation like this. You have now a network of learners. a network of learners, and they are seeing feature data and classes. This is the training data. Now they want to work together to find the separating hyperplane, right, by minimizing which cost? By minimizing this cost. In this particular example, all the individual costs are the same. So minimizing the sum or minimizing the cost is the same. So if you minimize this cost, you're going to find the logistic regression solution, right, which gives you a separating hyperplane. Well, just write down the diffusion algorithm or the consensus algorithm in this case, right? You have to compute the gradient of Q. So you remove the E for that. It becomes Q. Compute the gradient of this and write down the algorithm. Okay, so this is Q without the E. Compute the gradient, right? If you do the algebra, this is what you get. So this is, in this particular form, this is the ATC version of logistic regression. Right? So in this particular case, the agents are working together using their local feature data and training data to converge to a common separating hyperplane. Okay, so that's how this works. Okay, so it doesn't need to be mean square error cost, right? This is a more general form. Right? I'm repeating it here again, right? Okay, so this is what you get. Okay. Now, in the diffusion solution, if you come here, let's go to the statement again. If you come here, for example, in this particular implementation, what are the agents sharing? They are sharing the estimate, right? But they could share something more than the estimate, right? You can, and there are, by the way, many variations of this by now. Here, for example, you are combining all the estimates of your neighbors. But I may not need to do that. For example, at every iteration, I may select randomly a subset of my neighbors and combine their estimates if I want to reduce communications, right? You can do that. You may select only one of my neighbors randomly and do that, right? So there are many variations of this. One variation is they can share more information. If you can afford that, you can share more information. For example, agents could share their estimates, but they can also share the gradient vectors to improve the search direction along which they are moving. Okay? So for example, one other form of diffusion that you can do is like this. So for example, here, so I am an agent K, right? I'm agent K, agent K. Agent K. So here I'm combining the estimates from my neighbors just like before. But here, rather than move along the negative direction of my own gradient, let me combine the gradients from my neighbors again. Get a better estimate and move along that direction. Right? This is an enlarged form of cooperation. So now you have two sets of combination coefficients, not just A, but you also have another set of combination coefficients, C. Okay? You can again derive this form more formally. Okay, you have the CTA version and the ATC version, and then you can study the performance of these algorithms and so forth. Okay, now we are not going to study this. In one of the references I gave you, this is studied in some great detail. It's enough for us to focus on the case where this matrix C is the identity. So I only need one of these. It's enough for us to focus on that case. Okay. The analysis in some of the homework problems, you will be asked to study this case, okay? So, now, another way for you to interpret this result is just to think, so this is the matrix C, by the way. So the matrix C, the coefficients are non-negative, they add up to 1, and the matrix C will be right stochastic rather than left stochastic, okay, if you combine these conditions. Okay, you can show that C has to be right stochastic as opposed to left stochastic, okay? But this is a detail, we don't need to get into that, okay? You can think of the enlarged diffusion form as associating with each agent K and an enlarged cost function, which is the combination of the cost of its neighbors. And then you move along the direction of this, it's like moving along the direction of that, right? So that's why studying this is not that different from studying one that involves only its own cost. Understood? Okay, so that's why I'm going to focus only on the case when C is equal to I. Okay, that's enough for us. Fine? Okay. So I introduced three classes of algorithms for you: incremental, consensus, and diffusion, right? So let me give you some historical background and why the algorithm is called consensus, right? And why for adaptation and learning diffusion becomes necessary. Okay, and then I'm going to go back and discuss the original form of consensus that motivated the consensus form I described before, okay? So here, I mentioned consensus in my first lecture. In my very first lecture, if you go there, I talked about the original form of the consensus algorithm. The original form of the consensus algorithm did not deal with the streaming data. It dealt instead with the following problem, okay? Assume I have a collection of agents here. I have a collection of agents, n of them, and there is some topology linking them, right? So I have n agents, okay? And there is some topology linking them. And let's assume that each agent has some measurement. Let's call it, so decouple what I'm talking about here from what I talked about before, okay? I could have called this something else. I'm calling them W1 through Wn, okay? So let's assume that these agents, right, have some measurements. Let's say temperature measurements or channel measurements have some measurements. So this is a static problem. I have a connected graph. I have a collection of agents. And what you would like to do, you would like these agents to run a distributed algorithm and figure out what the average value of the state of the network is. If these measurements are temperature, you would like to know what's the average temperature over this entire network, but only through distributed cooperation, localized cooperation. Understood? So this is what the original consensus implementation does. It doesn't deal with the streaming data. It just assumes that you have a network. I have some data sitting at the nodes. That's it, fixed. No more data is arriving. I would like to know what's the average value of the data that's sitting in the network in a distributed manner. So what the original consensus does, and I'm going to prove to you later why it works, it does the following. It says, let's pick a doubly stochastic matrix A. What does doubly stochastic mean? Columns add up to 1 and rows add up to 1. For example, let me just give you an example. Let's assume I have a network here, okay, a network. I have two neighbors and myself 3. So I assign 1/3, 1/3, 1/3. Each one of you does the same thing, uses this uniform rule. He has 5 neighbors, 1/5, 1/5, 1/5. This uniform rule results in an A that's left stochastic. You can check, okay? So that's one example, one popular example of a left stochastic matrix. One example of a doubly stochastic matrix would be something like this. He's my neighbor. He has neighbors. Let's say he has 3 neighbors. I have 4 neighbors, okay? So what's his degree? 3. Degree is the number of neighbors. My degree is 4. So the weight I'm going to put between us is 1 over the maximum of the degrees between us. So the maximum is 4. So it will be 1/4. Okay. The second way of constructing the combination policy as a function leads to a doubly stochastic matrix. It's a very metropolis rule, it's called. Okay. You will see this later, but I'm just giving you examples so that you know that matrices like this exist. Okay. You construct them from the graph. Okay. So assume you pick a doubly. That's what the original consensus does. Pick a doubly stochastic matrix. For example, this metropolis rule that I just described. Okay. And let's assume that the second, I already know because it's left stochastic, all of its eigenvalues, right? The spectral radius is 1, right? So let's assume that the second largest, right, eigenvalue has magnitude less than 1. Because the largest one has magnitude 1. The spectral radius is 1, right? So what this is saying is, assume that there is only one eigenvalue whose magnitude as 1. The next to it is strictly less than 1. If you pick your A like this, okay, so you only have a network. What this is saying, pick an A that satisfies these conditions. I'm going to show you actually what these conditions mean is that make sure that your network is strongly connected. That's what this means, okay, but it's hidden here, but I'm going to show you, right? Just make sure that your network is strongly connected. Or a strongly connected network satisfies this condition, okay? Assume this is the case, then you can show the following. If your agents perform the following operation, each one of us has a W, right? So I'm going to combine the W's of my neighbors, and that becomes my new W at time I. Every other person every other agent is doing the same thing. You combine the W's of your neighbors, and that becomes your new W, right? So after one step, each one of us has a new W. Now repeat, I combine the W's of my neighbor, I'll get a new W at time I plus 1. Everybody else is doing the same thing, right? Then you can show that if your A satisfies the condition I showed, doubly stochastic and the second largest eigenvalue, magnitude less than 1, you can show that all of us will converge to the mean. Right? This is the original consensus. That's why it's called consensus. Everybody will agree on something, the W bar. You understand? Okay, so if we iterate long enough that process, no new data is coming in, right? Because if a new data comes in, then this changes. No new data is coming in. The data is fixed, and now you iterate infinitely often on that particular data. Using this process, you converge. You get the idea? This is what the original consensus is, okay? And we talked about this before, okay? So it was motivated by this idea, okay, that some works in the literature, okay, proposed using the consensus construction to motivate algorithms that respond to streaming data, okay, to respond to streaming data. What if I want to solve a mean square error estimation problem where data are arriving now at the agents sequentially, okay? So, for example, if you look into the literature, into the early literature, you are going to find implementations that look of this general form here. They look like this general form. They perform as follows, okay? You have a network. You have a network of agents, okay? First, remember, I'm looking at the network at time I minus 1. Every agent has an estimate, which I'm calling WLI minus 1. Okay, every agent has, you take a snapshot of the network, every agent has an estimate at time I minus 1. So they are going to iterate a few times, j times, using the traditional consensus iteration. Let's iterate a few times so that all of our W's get closer together. That's what the consensus result says. If this j goes to infinity, all of them will, right? This is what this is saying. You see, iterate over n, this n. Okay, so iterate a few times, j times, okay, until you get your network close together. So all of them are essentially close together now, right, for all practical purposes. And then each one of them, okay, each one of them runs a gradient descent recursion in response to streaming data. This is the original form. This is the original form of the consensus construction for streaming data. It generally looks like this, okay? Now, you understand the algorithm? Okay, now this is different from what I described earlier and what I referred to as consensus. Because what I described earlier, what did you have here? Agent K computes a weight by moving along the negative direction of its weight, and what you had here was the combination of your neighbors, right? Here instead, you combine the information of your neighbors, but you iterate a few times before you put it here. So you introduce this additional step where you have two time scales, right? In going from time I minus 1 to time I, in between you have to run j steps. You have to run j iterations, right? So the agents will need to be able to run at a rate that's j times faster than the I time frame. You understand? You have two time frames here. One, right? Data is arriving. So this is I minus 1 here. This is I here. In between, you should be able to run j iterations, right? Okay, and then this repeats. J iterations, right? So your agents need to be more powerful. I mean, run faster than needed, actually, okay? So this is one of the, so this was one of the motivations, the original motivations that motivated us to work on diffusion strategies. We wanted to see if we can do away with this intermediate consensus step, and would it be possible to devise an algorithm that doesn't require multiple steps. You can use the combination right away and still converge, right? And that's what actually the diffusion strategies do. They do away with this intermediate step, okay? So that was one of the motivations, okay? Now, also in most original works, you don't have a constant step size here, okay? Because in general, people were interested in solving optimization problems, conversion to the minimum, using a decaying step size. Like we showed earlier, if you put a decaying step size here, you can kill the effect of gradient noise, because since this is going to 0, it kills the effect of the gradient noise that comes from here. But that kills adaptation, because if the minimum changes, you will not be able to track it, because this term would have disappeared, right? So that's why I'm insisting on a constant step size here, okay? So this was another element, okay? Of course, since then now, you have this consensus form that I showed you before, which involves the same time step throughout. You don't have these j iterations in the middle anymore, okay? So that's okay. You can introduce that consensus iteration, okay? So we can remove the j averaging operations, okay? But like I said, most works still continue to use a decaying step size. But I'm interested in a constant step size because we want to do adaptation, right? So now if I remove the j operations and I make the step size constant, will that be enough? It turns out that for adaptation and learning, that's not enough because of the instability problem, right? When the step size is constant, okay, so if you come back here, if you remove this, just put the sum here, and so this removes the j steps, but now if instead of a decaying step size you use a constant step size, this is not sufficient. This is not sufficient because it can still show instability problems, as we are going to see later, okay? Because of the asymmetry. You are computing the gradient at one point, but starting from a different point, okay? So these facts were the main motivation for the introduction of the diffusion strategies almost 10 years ago or so, okay, where the updates are symmetric and the step size is a constant, okay? So this is what you would find, for example, for consensus. You start from here using decaying step sizes and a different point here than there, okay? You can even use, by the way, matrix. The step sizes don't need to be scalars. They can, like in RLS, right? You have a Riccati variable, right? Scaling the error. So you can also do things like that, okay? But this is just a remark for now, okay? So here I'm just giving you references in relation to this discussion, what motivated this work, right? That we would like to devise algorithms that can respond to streaming data. So I don't want to have two time scales. Data comes in, the network responds. Data comes in, the network responds. So I don't want to have two separate time scales. That's one. Number two, I would like it to be able to learn continuously. So even if the channel that I'm tracking or the unknown that I'm tracking changes, I would like the network to be able to track it. For that, I need a constant step size. But once you want the step size to be a constant, you need to ensure that your network stays stable, right? So these were the main motivation for the study of diffusion strategies of the CTA type or ATC type. And then there was one more element that we added, which is in the consensus result I introduced earlier, you need your A to be doubly stochastic, right? If A is doubly stochastic and the second largest eigenvalue is less than 1, then you converge to consensus. But our analysis of these strategies has shown that a left stochastic A leads to better performance. Okay, leads to better performance. Okay, because in the adaptive context, you see here, in the adaptive context, as you are going to see, okay, the W's at the agents are not going to converge to the optimum. Just like in any adaptive implementation, you don't converge to the optimum, you get close to the optimum, right? You get close. So what do? We assess how small the variance of the error is, right? How small this is as I goes to infinity, the mean square error or mean square deviation, right? Okay. As you are going to see later, this quantity can be made smaller for left stochastic matrices in comparison to doubly stochastic matrices, okay? So even though you are not converging exactly to omega 0 because of gradient noise, you will be getting very close to it, because this will be of the order of the largest step size in the network, as we are going to show, okay? And then the nature of the combination policy will matter, okay? It will matter. This is number one. The other thing that will happen is when you use consensus or diffusion to train these networks, in the stochastic gradient case, the agents will not converge and will not reach consensus anymore. You know, this idea that all the W's should go to the same omega 0 in the adaptive context does not happen anymore. All you can ensure is that all of them, okay, will get very close to the omega 0, and you can quantify how close. You'll get, all of them will get uniformly close to omega 0. All of them, right? If this is omega 0, right, they will drift around omega 0, and the size of the variance of that error will be of the order of the step size. So if all of them will enter a circle of size mu, right, if you measure the variance of that error, okay, but they will, because of gradient noise, they will be drifting around omega 0, but trapped within that small distance of omega 0. You understand? This is what will happen when you study these algorithms in the adaptive context, okay? But anyway, all these statements that I'm making now, they will be made formal, right, in the next lectures. I'm going to derive these results analytically for you. I'm just trying to motivate them, okay? Yes?
As compared to the previous consensus algorithms like you showed,
yes,
the current consensus algorithm, is it faster or is it slower?
Faster than what?
Than the previous, the one that uses J steps initially and then adapts.
No, okay. Of course, if you iterate many times between two updates, right, you are already exploiting the information more fully. Of course, that it will converge, for example. It can give you better performance, right? But it will not be a real-time adaptive solution. Okay, you understand the difference? Similar to the incremental. Similar. That's why I had to use mu over n and mu. Here, if you want to match the convergence rates, in the solution that uses j steps, you can use a different step size than the solution that uses only one step to make the comparison fair. You understand? Okay. Anyway, so this discussion is just meant to motivate you why we do things the way we do them, okay? If you are interested in more technical details, you can read the text, okay? Fine. So let me come back to the original consensus strategy and explain to you why it works. The original one where agents reach consensus, right? Which is a very interesting result if you think about it, right? I have a network of agents, they have pieces of information. How come if you just work locally, you can converge to the average across the entire network, right? It's an interesting result. So this part of the lecture is based on this appendix from that reference. This is a book chapter which you can download from my website. Okay, so again, let's go back to the problem. I have a network. Each agent has some measurement, could be vectors, x1, or I called them w1 in the previous slide, right? This is a figure from a different slide, okay? And I would like to find what the average value is, right? Okay, the notation changed slightly, okay, just because this is from a different reference, okay? So the agents have x's, they are fixed, they are not changing, but I would like them to work together to converge to the average, and the average, I'm calling it omega 0, the quantity I want, right? So the way consensus works, okay, like I said, you pick weights that add up to 1, non-negative weights that add up to 1, okay, as usual, right? So the matrix A is left stochastic. Actually, in this particular case, we will require it to be doubly stochastic, right? Okay. And you perform this iteration. So at every iteration n, every agent k combines what exists in the neighborhood. And every agent is doing the same thing. You just keep repeating this infinitely often, okay? So this is the state of agent k at time n. So you look at the state of your neighbors at time n minus 1, okay? So now you have a network, and each agent is updating its state vector according to this. I can rewrite this more compactly as follows. Let's define a long state vector which contains the w at each agent, right? If I look at time n, I will see these w's. If I look at time n minus 1, I will see these w's. And there is a relation between this vector and that vector. You just get it from here, right? It's a first order recursion. So here it is. Let's define z sub n. This is the state of the network at time n. Of course, the initial condition will be x1, x2, xn, right? That's where you start from. The recursion for w translates into this recursion for z. Z now is a long vector, right? This is the new z, is the old z times some matrix A. What is this matrix A? It's the combination matrix. But remember, the combination matrix is n by n. But this z, right, each one of these w's, this is a block vector. Each one of the, you have n of them, and each one of them is m, right? So that's why the A that appears here is not the original A, but the extended A. So this calligraphic A is the original A, Kronecker product I, M. That's all. You know, this is just simple algebra for you to check that because this is a long vector that has blocks of size m, I have to take each entry of A, this is Kronecker product, each entry of A, right, enlarge it to an identity matrix of size m, right? So this is, becomes a, A11 becomes a diagonal A11, A12 a diagonal A12, right? So it becomes A transpose times that, okay? So this is the dynamics of my recursion, okay? Starting from a fixed initial condition. And now I keep iterating. What do I want to show? I want to show that the Zn, as n goes to infinity, all of its entries will become the W0, right? So what I want to show is that, so this is the A, okay, so I want to show that the Zn goes to something that looks like this, W0, W0, right? So one way to write this is to say, this is the column vector of 1s, Kronecker product W0, correct? Right? You take the number 1 times omega 0, then the number 1 below it times omega 0, right? So, is this correct?
This is the same as saying that we have to prove that that is the Perron eigenvector.
Of what? No. I'm just talking about the vector for now, right? Yeah. For now, I want to show that this vector here, z sub n, converges to a vector whose entries are the same. All of them are the same, right? I'm just writing it in a compact form. This is a vector, okay? A compact form to write it is to say 1 Kronecker omega 0, right? Okay? Now, what is this omega 0? This is now just some algebra here, okay? So I'm just introducing some notation, and then I'm going to prove that result, okay? Some notation. What is the omega 0? The omega 0 is the average of the x's, right? Okay. Now, what is Z0? Z0 has the x's. You know, I just want to explain that this notation is not difficult, right? These are the x's, right? What is 1 transpose chronicle I? It will be a block column with I, right? That's what it is, 1 transpose chronicle I. When you multiply that by the x's, you are adding the x's, divide by n, right? So this is just a fancy way of writing what omega 0 is. 1 over n, the sum of the x's, right? You understand? This is the 210b level of writing the expression, right? The other one is the 210a. Okay, 1 over n, the sum of the x. Okay, you will understand why I write it in this form, because since I have chronicle products in A, it will become easier to handle the analysis. Okay. Of course, at every iteration, another way also to try to prove the result, rather than show that this is going to that, is to show that the error, right, this is the difference between where you want to go and where you are, that this error is going to 0, right? Or the vector of errors is going to 0, right? This is another way to show it, right? Okay. Okay. So this is the vector of errors. I call it W tilde n. I could have called it Z tilde n. Perhaps I should have done that to be consistent, okay? So what is the vector of errors? This is the Z, which has the vector of omegas, and this is the vector that has omega 0, omega 0, omega 0, omega 0, correct? Fine. So I want to show that this omega tilde goes to 0. Okay. So now, if I find a recursion for omega tilde that looks like this, omega tilde n is some stable matrix times omega tilde n minus 1, then I would have proved my result, right? That's what I'm going to do next. Show that this W tilde n satisfies a first order recursion with a stable coefficient matrix, right? So that the algebra now will be that, okay? Okay. So you see, it's not difficult, but because I have a network and I want to study the evolution of the network simultaneously, I have to introduce these block vectors. And this will happen throughout this course for the remaining lectures. Whenever we study the performance of networks and the evolution of the dynamics of the network, I will always need to introduce a state vector like this that collects the errors from across the network into a big vector, and then study the evolution of the vector, rather than study the evolution of every individual error at every individual location. We will do it together, understand? So what you are seeing here, this concept will be repeated later, okay, that we define these extended vectors and study their evolution, okay? So this is the famous, okay, result about the convergence of the consensus iteration, right? So that whole body of work is based on this theorem, okay? And this is what the theorem says, okay? This theorem, I think, is from 1974 or so by de Groot, okay? It's a famous paper by de Groot, okay? And this is what the result says, okay? The consensus iteration using static information converges if and only if. So this is a two-way, two-sided statement, right? If and only if A is doubly stochastic and the spectral radius of this matrix is strictly less than 1. Okay? We are going to see that this translates into that other condition that I showed you, that the second largest eigenvalue in magnitude is less than 1. Okay? But this is how the statement is usually stated. Okay? So, I told you that we have to pick a doubly stochastic A, and there is a condition on the spectral radius of this matrix. Okay? So let's prove that this is the case. So if this happens, W tilde n will go to 0, and this is if and only if. I have the proof now, okay? So I will go through the proof with you, okay, and before I conclude. Okay, so let's prove it. So just linear algebra, okay? The proof is not very difficult, just linear algebra. And you are going to see, when we study networks, very often we are going to use chronicle products, because you have to extend these vectors, and chronicle products come up naturally. Okay? So before I do the analysis, let me remind you of these properties of chronicle. You know what the chronicle product of two matrices are, right? You take each individual entry of E11, you replace it by E11 times B, right? E12 times B, right? That's what it does. So this is one property of Kronecker products. If you compute this matrix to the power n, it's like computing the Kronecker product of the powers of v and b. Property, you can prove it, okay? This is a property. Another one, if you compute the product of two Kronecker products, it's like the Kronecker product of the individual products, EC, BD. This is a very useful property. And here, sum Kronecker C, you can do the sum of the individual Kronecker products. Okay, so I'm going to use these properties. Okay, so let's do that. First of all, equations 6 to 3 and 6 to 4 are obvious, and this is what they say. If a matrix A is doubly stochastic, then the nth power of A for any A is also doubly stochastic. Because you see, let's consider A squared. What is a doubly stochastic matrix? A times 1 is 1, and A transpose times 1 is 1, right? So here, let's say take A squared times 1. Well, this is A times 1, which is A times 1 again, which is 1. And then you can do the same thing for the A transpose. Any power of n will be doubly stochastic. So that's first conclusion, okay? So we will use this. The second, okay, this you can prove by induction. For example, the nth power of this rank 1, this is a rank 1 modification of A, right? This is a rank 1 matrix, okay? The nth power has this form. The nth power of A minus the same rank 1 modification. Because A is doubly stochastic. You see, just take a simple example. A minus 1 over n, 1 transpose squared. So that will be what? A transpose minus 1 over n, 1 transpose, right? Expand it. So you will get A transpose squared. So that's A squared transpose minus A transpose times 1 over n, 1 transpose, right? A transpose times 1 gives you 1 again. So minus 1 over n, 1 transpose. The same thing for the other side. 1 transpose. Then plus 1 over n squared, 1 transpose, 1 transpose. Is this too fast for you? Okay. Now 1 transpose is, and cancels that n. So this term cancels one of these and you are back to that, right? So you can now prove it by induction. Okay, so these are just linear algebra relations I will need for the argument, right? Okay, so I proved these two statements. So let's continue. The next result I need. Okay, the next result I need, because this matrix is when I'm going to derive a recursion for W tilde n, that big vector of errors, this matrix will appear. So first I want to show that this matrix, I can write it in a certain form, using properties of Kronecker products. Okay, so where this comes from, you'll see it very soon, okay? So take this matrix. Remember, A by definition is the Kronecker product. By definition, this calligraphic A is A Kronecker product I. So A to the n is this to the n, which we know from properties of Kronecker products is this, right? So that's why you have this. Okay. But now I showed you, right? I showed you that B plus C Kronecker D is B Kronecker D plus C Kronecker D. So that's how that property I used to group these, to rewrite this like that. Understood? Okay? So you see this Kronecker I took it out. Okay? But now I just proved this result on the previous slide, right? That this quantity here is actually the nth power of this, right? Kronecker that. Okay. Well, again, use the property of Kronecker products. I can take the power out, right? I can take the power out. So, okay, I showed that matrix can be written like this. Fine so far? Okay. So I proved the 3 auxiliary results that I will use. That's all, okay? Why did I think of this matrix? Because it comes up and then okay. So now let's go and establish what we want now. Okay, we are almost there. Remember that I showed this recursion, Zn is A transpose Zn minus 1. So if you iterate it, you get this. Just iterate it, right? You get n of them, right? Very good. So what is the error? The W tilde n, right, is the vector. How did I define it? Is the, is 1 Kronecker omega 0, right? This is the vector of all omega zeros minus Zn, right? That's what W tilde n is, the big vector of errors. Okay? So here it is, minus Zn, here it is, minus a to the n transpose Z0. Fine? Okay. 1 Kronecker omega 0, remember that I showed you the 210 version of omega 0, right? 210b version of omega 0, right? Which was this one. Okay? Omega z version, omega 0, right? Rather than write 1 over n, the sum of x's, it is 1 over n, a Kronecker product times z0. I want to write everything in terms of z0 so that I can take z0 out. Okay? So that's what you have here. You see? This omega 0 here is 1 over n, 1 Kronecker I z0, something like that, right? Okay? So you can see here, that's what I wrote down here. You see 1 over n. You see here 1 transpose. What do I have here? Did I, yeah, here should be 1 transpose, right? 1 transpose, okay? 1 transpose, correct, okay? Anyway, so continue now. But remember, this is exactly the matrix I showed you on the previous slide, that it can be written like this, correct? It can be written like this, okay? Therefore, I showed that W tilde n is some power of a matrix times Z0. Let's look at this matrix inside here. What are the eigenvalues of this Kronecker product? They are the products of the eigenvalues of I, which is 1, times the eigenvalues of this. What are the eigenvalues of this matrix? The spectral radius by assumption is less than 1, right? The spectral radius by assumption is less than 1. So this matrix is stable, right? And therefore W tilde n goes to 0, right? So we proved one direction. We used the fact that A is doubly stochastic, right? And we used the fact that the spectral radius of this is less than 1. So all 3 conditions were used, right? Okay. So let's now prove the converse statement. Okay, the converse statement. Okay, sorry. The converse statement. Okay, the converse statement is I want to show if convergence occurs, then the 3 conditions have to hold. A is doubly stochastic and the... Okay, so let's assume... Okay, so let's assume that Zn is indeed converging to omega 0, omega 0, omega 0, omega 0, right? Very good. But Zn, right? So this means that this limit is converging to that, right? Because Zn is A to the n transpose Z0. So it means that this limit, right, is converging to 1 Kronecker I omega 0, which on the previous slide, right, we expressed it in this form, right? That's the form where I was stuck, and you will check it, okay? Fine? Okay. So, if convergence occurs, then this is equal to that for any Z0, right? This has to be true for any initial condition. For this to be true for any initial condition, right, you can eliminate Z0. So this limit has to be equal to that limit. You see, this times that becomes this. Correct so far? Very good. Okay. But remember that this A is A Kronecker I, right? So if you remove the Kronecker I, this limit becomes what you have here in the 3rd line. Okay? Okay. So we conclude that this has to hold. Correct? Okay. Well, if I multiply by A, this same thing has to hold. Correct? Okay. But this limit on the left, which is the limit of a to the power n plus 1, is the same as the limit of a to the n as n goes to infinity, correct? Okay? So, this limit is the same as that. Therefore, this has to be the same as that. Okay? Therefore, A transpose times 1 over n 1 1 transpose has to be equal to 1 over n 1 1 transpose, correct? So if you write down this equality, okay, if you write down here it is, 1 transpose, you take it out. But now look here, 1 transpose is a row vector. This is a column vector. Column times a row is a matrix. It will be 0 only if this column vector is 0. So A transpose 1 has to be 1. So A has to be left stochastic. You repeat the argument by multiplying by A from the left, from the right instead. Here we multiplied by A from the left, right? You can repeat the argument by multiplying from this side instead. Okay? And you will conclude that A has to be right stochastic. You put them together, A has to be doubly stochastic. So if convergence occurs, A has to be doubly stochastic. We still have to show the third condition, right? So what is the third condition? Okay? Because here, you see the error. So for convergence to occur, okay? So if I go back to equation 624, right, we showed this before, okay, that the error evolves, right, with this coefficient matrix. If the error goes to 0, this coefficient matrix has to be stable, okay. For this coefficient matrix to be stable, its row spectral radius has to be less than 1. Understood? Okay. Very good. Okay. Here it is, right? We already know that the error evolves according to dynamics that's determined by the spectral radius of this. If we are saying it converges, then this has to be stable, right? So its spectral radius has to be less than 1, right? So if I go back to the statement, this is what we proved, okay? This is what we proved, that the consensus iteration converges if and only if these 3 conditions hold, okay? A is doubly stochastic, and the spectral radius of this rank 1 modification of A is less than 1, strictly less than 1, right? And this is if and only if. Fine? Okay, so this is what motivates the consensus construction, that if you choose any A that satisfies these conditions, all nodes will reach consensus, will reach the average value, which is a very interesting result, right? So if I can elaborate a little bit more, okay, let's try to understand this a little bit more, okay? So just, okay, what is this spectral radius? Let's look at this matrix. Let's denote the eigenvalues of A by lambda 1, lambda 2, lambda 3, lambda n, where lambda m is the smallest in magnitude. What is the largest eigenvalue of A in magnitude? Okay. It has eigenvalue. We know it has eigenvalue at 1, right? So the largest one is 1. Okay. So I know that the eigenvalues of A satisfy this condition, right? All of them have magnitude less than 1. The largest is exactly 1. Okay. But now, what are the eigenvalues of this rank 1 matrix? If a matrix is rank 1, what are the eigenvalues? 1 and all zeros, right? Okay. Because the norm, if you take the norm here, 1 transpose 1 divided by n, that's 1. That's the eigenvalue, by the way, of x, y transpose. It will be y, okay, it will be y transpose x. Okay, you can check it. So this matrix here has eigenvalues 1, all zeros. And the eigenvalues of this rank 1 modification of A, okay, you simply subtract that 1 from the maximum eigenvalue, remove it. Okay, so the eigenvalues you can check of this rank 1 modification of A, they will continue to be the same eigenvalues of A, but that maximum eigenvalue becomes 0. Is replaced by 0, right? This is simple to check. Just check. Simple algebra. Okay? Introduce, for example, any eigenvalue, eigenvector pair for A, and you will see that they will be eigenvalue, eigenvector pairs for this matrix with these eigenvalues. Okay? Understood? Okay. So now, the requirement that the spectral radius of this is given by what? By the magnitude of lambda 2. So what we are saying is that we would like the magnitude of the second largest eigenvalue to be less than 1. Right? So this is the same. Right? I'm just restating that condition in this other form. Okay? Now, okay? And remember that W tilde was converging to 0 at a rate that's determined by the eigenvalues of this matrix, right? Right? Didn't we show that? Here. The error is converging to 0 by the eigenvalue, according to the the rate of convergence is determined by the eigenvalues of this matrix, which are determined by the eigenvalues of that matrix, right? Which one is the slowest converging mode? Right, which is lambda 2, right? Lambda 2. So that's why for the consensus iteration, it is the second largest magnitude eigenvalue that determines the rate of convergence, right? Not the largest, because the largest is 1. And the largest does not have any influence on the convergence rate because of this rank modification, right? So it's the second largest eigenvalue of A that determines convergence, right? So for example, you can formulate problems. Let me try to find the A whose second largest eigenvalue is the furthest away from the unit circle. If you want to speed up convergence, for example, you can formulate problems like that, okay? Okay. So now you know what the rate of convergence is. So the rate of convergence is determined by this quantity here. Not lambda 1, but lambda 2, right? Okay. One other thing that follows. If your network happens to be primitive, strongly connected, if your network happens to be strongly connected, okay, meaning you can find a path between any two links and there is at least one self-loop, at least one AKK that's positive, okay? Then we know that A will be primitive. Then we know from the Perron-Frobenius theorem that this A has a single eigenvalue at 1 and all other eigenvalues will be strictly less than 1. And therefore, in particular, this will hold, okay? So therefore, a doubly stochastic combination matrix over a strongly connected network will make consensus converge, right? So that third condition, essentially, if you say instead of it that you have a strongly connected network, the conditions will be met, right? Because this will be met, and I just showed you that this is equivalent to that third condition, okay? Okay, so that's this statement here. Any doubly stochastic matrix and primitive, and therefore over a strongly connected network, will satisfy the three conditions, right? And therefore consensus is going to converge, correct? Okay, so that's what I wanted to discuss with you today. Okay, so what I did today, I introduced three classes of algorithms, right? Incremental, consensus, and diffusion, right? And then I said we're not going to focus on incremental for the reasons I explained, right? It has some, it encounters difficulties when you try to use it in the context of an adaptive implementation, right? If edges break down, the solution will break down. You have to find a cycle. You have to cycle over all of your agents before the next time instant, right? So these are difficulties, okay, that the incremental solution encounters. So we move to consensus, right? And the consensus iteration, all agents can run the consensus iteration at the same time, right? One of the inconveniences is that it has an asymmetry in its update. And that asymmetry can cause instability, as you are going to see. So we moved from there to a diffusion implementation. Adapt then combine, or combine then adapt. And we are going to see later that this resolves the instability problem and also leads to improved performance, okay? And then I moved on to tell you where the consensus iteration or terminology comes from by going back to the original consensus implementation, right? Whose purpose is to find the average of static information distributed over the network, right? If you simply iterate the traditional consensus iteration, I proved that if three conditions are satisfied, and these are if and only if conditions, right? A has to be doubly stochastic, and the second largest magnitude eigenvalue has to be bounded from. If these conditions are satisfied, then it converges, and the rate of convergence is determined by the second largest eigenvalue. That's what the traditional consensus implementation is. It doesn't respond to streaming data. To respond to streaming data, you have to use the iteration I showed you before, right? And if you want it adaptive, you have to use a constant step size. But then that can create some issues, which we are going to address later, okay, by using the diffusion strategies, fine? So this lecture was meant to introduce you to these strategies, okay? And then we are going to study them now more and more closely in the next lectures, okay?